and welcome to the processor instruction set. So in this homework we're going to look at how the processor instruction set works, going by the syllabus statement that are in homework 4 in your booklet. So the instruction set is part of a computer that relates to the programming. So this is in the machine language. So as you know, the machine language is a low-level language. Now, know the difference between high-level and low-level. High-level language is the language that is closer to English, and low-level language is the language that the machine will understand, which is effectively ones and zeros. Now, the instruction set will provide the command to the processor to tell it what it needs to do. So as you know, the processor is a very, very complex chip inside your computer, and it is effectively the brain of the computer. So now what does the instruction set contain? Let's take a look at this. So addressing modes, instructions, native data types, registers, and the external input of the input and output devices, the exception handling and the interrupts, along with memory architecture. So all this now all goes on inside your computer. So what it will do is add two numbers together, then it compares the numbers, then the input information from the device, such as the mouse or the keyboard, will go into the computer, then it will jump to the designated RAM address, and then there's a condition that it will jump if the condition statement that jumps to a designated RAM address. So this is when all these instructions are being processed. Then it loads the information from the RAM to the CPU, and then basically that provides your output information, okay, to a device such as the monitor or the speakers or printer, whatever. And then that information needs to be stored in the RAM. Okay, so all of this will go on inside your computer when you're just doing something as simple as typing something, opening something, using your mouse, and so forth. So what are machine code instructions? Now, the machine instructions are commands or programs written into a machine. Okay, so it's the code of the machine. So that's the computer. And then it will recognize those instructions and execute. Okay, so now it's made up of several bytes of the memory, and it tells the processor to perform one machine procedure. Okay, so like one instruction at a time. So the processor then looks at the machine instruction in the main memory in sequence, and then performs one machine operation for each instruction at a time. Okay, so obviously these instructions have to be sequenced, okay, to stop a bottleneck or to stop, you know, one thing happening before the other. So then the group of instructions is the main in the memory is called the machine language program. So you're going to get one instruction at a time. Then when all these are sort of grouped together into a bunch of ones and zeros, then that's the machine language program. So what are machine code instructions? Now, the machine code is the only language that the processor recognizes. And as I said, it is a low-level language. Okay, so we've got your brain here, you've got your brain of the computer, which is the processor. And then the processor, basically, just to put it in simple terms, a whole bunch of ones and zeros goes through it. Okay, and then that creates something more complex that you will understand. So the typical machine code will look like this. As I said, just a whole bunch of ones and zeros that all go through that processor. And then what appears on your computer in front of you, okay, which could be an icon, it could be a video, it could be a PowerPoint like this one, for example. So it is essentially impossible for people to understand, but yet incredibly efficient for your processor. So each different type of processor will have its own set of machine instructions. So that's why you've got some processors that work faster than others. There's different types of processors out there, as you know. So there's processors that will be made for gaming computers. There's processors that are made for high power computers that need to execute instructions very, very quickly. So a typical machine code instruction is in a simple processor, might occupy, say, 2 bytes. So here we go, we've got the opcode, then you've got the register, then you've got the operand. Okay, so opcode, so this is the basic machine instruction for an operator, and what it does, it will basically be add, load, subtract, divide, and so on. Then you've got your operand, and that is the value, okay, to be operated on, and the address value that will be operated on. So this is the value, this is the address, this is where it needs to go, this is when it needs to be executed. So, as I said, different CPUs, different instructions. Okay, so I suppose different people have got different capabilities in their brains. So the different processors have different instructions, okay, or sets of instructions connected to them. So even if 2 different processors have the same instruction, the instruction will be, well, executed differently. Okay, so it's a bit like, for example, if you're a fan of sports, for example, with footballers, there might be one footballer that's played in a certain position, then this new footballer comes along and plays in that position, and they're effectively playing in the same position, but they do things differently. Okay, so the machine code will be different, but the structure will be similar. Okay, so now when we've got our assembly language, which is machine code, okay, so which is, as I said, effectively is assembly language. The machine code tells the microprocessor, so that's the CPU, step by step what to do. So for example, move data from register A to register B. Now every microprocessor has its own set of machine code, and it's called an instruction set. Then we've got the data movements. Now the data movement instructions move data simply from one place to another, okay? So the source operand to another place called the destination operand. So we get it from the source, then it has to go to its destination. So the data movement instructions can be grouped into loads, stores, moves, and immediate loads. There are 2 types of instructions that involve loading data into a register and out of the memory. Okay, so here's an example table. So I'll come back to the example table. So it's all we've got to think about really is that I know this sounds kind of complicated and overwhelming, but it's all we've got to think about really is that all our computer's doing is just moving a bunch of 1s and 0s from one place to another. Okay, so it works. So our processors simply can only process a bunch of 1s and 0s. And those 1s and 0s can be interpreted, and they're just interpreted so they go from the source to the destination. And that's it. That's effectively what it does. So now for us to make sense of this, and obviously this is not what a computer looks at, because a computer just simply looks at 1s and 0s. So we've got our instructions here. Now, so you've got your LDM, which is immediate addressing and loading. Okay, so it will load, say, an N, which is 0011100001 to the address accumulator. Then you've got an LDR, which is an immediate address loading. So, and it's going to move it from one place to another. Then you've got your LDD, it has an address. Okay, and then that loads onto the accumulator. You've got your LDI, so it's an indirect address and load into the accumulator. So if we just look at this, so if we just look at all these operand codes here, what are they doing? They're going from one place and then they're going to another. That's all they're doing. Data moves from one place to another so the computer works. Okay, it doesn't need to be really thought of any more complicated than that. Okay, so we've got our abbreviation here, and it would obviously be an actual address. The N, as I said, will represent, the denary value really. Okay, so like 200 or something. And then this indicates an accumulator. Now let's look at decode and mnemonics. So LDD, so this is direct addressing, and it will load the contents of the accumulator. Then you've got your LDI, which is direct addressing as well. This has a given address, and it will load the content to the given address to the accumulator. And then the LDX, which is given an address. So this is indexed addressing, and it takes the content of the index register and it goes to the accumulator. Okay, so let's explain this instruction. So now, if you look in your book, obviously we have to have an example of transfer register notation. Okay, and so this stands for current. This is a 16-bit address that needs to be examined to identify the location of the data in the memory so that they're transferred to the accumulator. So obviously, so this is the current instruction register. That's the 16-bit address, and it is going to the accumulator. So that's all that means. Now, so here's some more examples of the arithmetic operators. So the add is the address content that needs to be added to the accumulator. Then the inc is the increment, so it increments the value by 1, okay, and stored in a specified register. Then you got your DEC, and that's a decrement, okay, so then that'll take 1 from the value, okay. Then we've got the comparisons and the jumps, okay, because some instructions need to go before others. So the program may need to jump unconditionally, or if it has a condition, the condition has to be met. Okay, so compare. Does it have a condition? No, make it jump. Does it have a condition? Meet that condition, then it can jump. Okay, so as you said, the condition has to be met, and then that will be flagged by the register. So once it's met and it has been set or not, then it can go. Right, so this is an example of a jump. So we've got the jump to the specified address. Then we compare it to the accumulator content with the address. And if the value is compared and it's been met, then it can go. So the JPE is the jump to the address based on a condition if true. Okay, so jump to the specified address, compare it. Is there a condition? And then if the condition's met, then it can go. Okay, then if it, and basically, then it can't jump if the condition is false. Right, so now we're going to take a look at some ASCII values. Okay, and well, we're going to look at basically the inputs and the outputs of these instructions, okay? So the instruction is collected to the opcode and then stored in the ACC, okay, so the accumulator, and it has an ASCII value, and it's typed out, which is basically typed from the character on the keyboard, as you know. So the instruction with the opcode out is used to display the character from the ASCII code stored in the accumulator. Now, this is using a worked example in the book, okay? So, we've got our registers here, and we've got our addresses. So these, and then what happens is these get traced into 8-bit values, okay? So, number 100 is the LDD 201, okay? And then these basically have all got these addresses. So then what happens is these addresses then get put into these values here, and these are the contents of them in the 8-bit value. So 200 would say be a bunch of zeros, then you've got 201, and then as you can see, they increment by 1 each time. Okay, so that's all that happens there. They increment by 1 each time. Now, what happens here is the program counter. So this will be when the instruction's set, and this is what happens after the instruction has been executed. Okay, so what the accumulator does is the accumulator will basically record how many instructions are in the accumulator. So when it's set, it's 0, 0. Then after it's executed, you can see the values change. But in some cases, the values may stay the same. Now, this is probably because if a condition has not been met, then the values cannot change. So until the value is true, then the value will change. Okay. Hopefully that has helped you. Thank you for watching. Please complete the instructions, the tasks in the booklet, okay, for the homework. Subscribe to my channel and like my videos, please. For teachers, for resources, you can visit my shop on Tess, and also you can follow me on Twitter at MissPriceCSCI. Thank you very much for your time.